The title is Pedestal Waveguide Architecture, based on rare earth ions doped lead and germanium oxides core decorated with gold nanoparticle island. A review. I am from Brazil, São Paulo, from Faculty of Technology of São Paulo. First of all, I'd like to thank you for the invitation. I'd like to congratulate you for the organization and I also like to add that this is an important initiative for those that work with optics, with photonics, mainly in this difficult moment that we are having due to pandemic. So I think that it really presents a motivation for all of us. Thank you again for the invitation. Here I show you an outline. This first slide intends to show you the plan of my speech. First of all, I'm going to talk about the motivation for the use of this material to produce the waveguide core. I'm going to give you examples in books. Then I will talk about waveguides production. Finally, a review of recent results that were already reported in the literature. The search for new materials with metallic nanoparticles has grown due to several applications for different technological purposes. In this context, plasmonics appeared as a new science to explain these metallic nanoparticles and their interaction with the incident light that creates the localized surface plasma, which is the well-known collective oscillation of free electrons in the metal surface and the appearance of this strong local field that surrounds the nanoparticle. When we approach the rare earth ion to this local field, the luminescence can be enhanced, and of course this growth depends on several parameters that are listed here. The excitation wavelength, the size and shape of the nanoparticles, the host, the distance between the nanoparticles and the rare earth ions, the concentration, and the largest effect, the largest enhancement takes place when both frequencies, the one of the incident light and the rare earth luminescence, approach the one of the surface plasma resonance. Although my talk will focus on waveguides decorated by island of gold nanoparticles, I'd like to briefly show you the motivation for the use of this material. They exhibit large transmission window from visible to near infrared to mid infrared, low melt temperature with respect to silicates to borates, high chemical stability, normally high refractive index around 2 or more, low phonon energy with respect to borate phosphates, and this represents an important characteristics because it provides low non-radiative losses, an important feature for the upconversion process. They demonstrated to be adequate hosts for rare earth ions incorporation, for metallic nanoparticles nucleation, and their enhanced linear and nonlinear optical properties reported by us in several reports showed possible applications that are listed here: color displays, optical amplifier, ultra-fast response devices, and cover to enhance silicon solar cell performance. I also like to highlight this book from Elsevier that I edited with Professor Sid, in which you can find some of these results. Well, now I'm going to show you very quickly some of these results obtained in books and that motivated the research with the optical amplifiers. We use the well-known melt quench technique to prepare these books, whose steps are shown here. First of all, we have the mixture of the reagents, after that the melting, the quenching in a preheated press mode, and finally the annealing. The annealing is performed to reduce internal stress and also form the metallic nanoparticles by thermal reduction. Now some of the results are mentioned obtained with this material. This was the first demonstration of the combined effect of the enhanced local field of silver nanoparticles and the efficient energy transfer between ytterbium and airborne ions that provided the strong green light. This procedure can be extended to different rare earth ions to improve the luminescence glasses efficiency and optimize display's performance. And this was reported some time ago, as can be seen here. It was possible with this material to demonstrate white light generation and color change controlled by silver nanoparticles using this material and three different rare earth ions that are shown here: ytterbium, thulium, and holmium. It was possible to obtain a strong white light, strong green light by specific combination of these three rare earth ions and the silver nanoparticles. There is always a mismatch between the solar spectrum and the silicon solar cell absorption, and a way to overcome this problem is based on covering the silicon solar cell with a luminescent material that makes use of the down conversion process. That motivated by this interesting result that can be seen here, in which you observed an enhancement of about 70% for this important emission of europium, centered at about 600 nanometers, attributed to the presence of these gold nanoparticles with size around 8 nanometers, we decided to use this material to cover a commercial silicon solar cell, but varying a little bit the concentration of europium, the concentration of gold. And then we obtained very interesting results, the best result that shows us efficiency increase of about 18% when the silicon solar cell was covered by the material that exhibited the largest luminescence, this one that I showed before, due to this strong red light that was emitted. So this proof of concept results indicate a way to evaluate the potential of the material to optimize photovoltaic devices performance. Moreover, this procedure can be used to different materials, organic or inorganic materials. A report about this was obtained recently by our group. Well, regarding the waveguides fabrication, I'd like to say that we use this sputtering technique to produce the thin films that form the core of the waveguide. The core is the place where light is guided. And of course, in this process, we need targets. Most of the targets produced by us, others are bought. And here I show you the steps used to produce one of the targets. And in this figure, the compact sputter system that we use for the production of the thin films. In this figure, I illustrate you the inside of the sputtering chamber. The sputtering chamber operates in vacuum with plasma of argon. And the substrate where the thin film is grown is placed above the two electrodes where the targets are placed. Target of gold and the target of the host. We use different architectures to fabricate these waveguides, the pedestal architecture and the rib architecture. However, the most recent pedestal waveguides were fabricated using the pedestal platform because of the advantages I'm going to discuss now. To produce this pedestal waveguides use the silicon technology, I mean the conventional microelectronics procedures that make use of lithography and etching, all of them performed in clean room. And we have two main steps for that. The first step is the preparation of the silicon dioxide pedestal in blue, shown here in blue, and the last step in green and yellow, the deposition of the material of the core followed by the deposition of gold, both performed by the sputtering technique. Of course, in this configuration, light guidance is possible due to the total internal reflection of the light That's attributed to the high contrast between the refractive index. We have 1 for the air, around 2 for the core, and 1.5 for the silicon dioxide. As I said before, the pedestal platform has advantages with respect to other platforms, mainly to the rig one that we used in the past. In this case, we have to etch the material of the core, and this is not an easy task, mainly when we deal with heavy metal oxide materials, as is our case. So, the pedestal platform represents an interesting alternative because we prepare the pedestal waveguide and then we deposit over it any material we want, and we do not have to etch the material of the core. We have different procedures to prepare this pedestal waveguide. One of them that uses the chromium mask and the other one that does not use. I will start with the one that uses the chromium mask, and I show you in this slide the several steps used for this fabrication. First of all, we have the growth of the silicon dioxide film, followed by the chrome film deposition and mask definition of the photoresistor, chromium mask definition, 3 steps to etch the silicon dioxide, and finally, the chromium removal. As I said before, the last step is the core deposition. When we use the chromium mask, we have the well-known micromasking effect, which is the columnar growth that surrounds the core and that compromises the guiding. In order to attenuate this effect, we reduce the thickness of the chromium mask by 70%, and we increase the number of steps to etch the silicon dioxide pedestal. In our case, we use 3 steps. And we finally obtain this better profile that can be seen here. Both images were obtained by scanning electron microscope. When we do not use a chromium mask, we have some advantages. Here are the steps for this fabrication: the silicon wafer, deposition of silicon dioxide film, spin coating of the wafer with photoresist, photolithography, etching of the silicon dioxide, plasma etching of the silicon, removal of the photoresist, wet oxidation of the silicon substrate. As like the other case, the last step is the deposition of the material. Unlike the other case, here we have 2 etchings, one for the silicon dioxide, and the other for the silicon. And the advantage in this case is that, as we do not use a chromium mask, we are not going to have the micromasking effect. As a consequence, we have this interesting result that shows us the results of propagation losses in 2 different conditions: when we use the chromium mask and when we do not use. And we can see clearly that we have a reduction of the propagation losses, and this represents an interesting advantage that in fact increases the waveguide performance. But regarding the production of the island formed by gold nanoparticles, as I said before, the island of gold is performed using the sputtering technique. So we deposit gold on the top of the waveguide. However, some special points deserve attention here. In this figure, I show you the inside of this sputtering chamber, the target of gold, a commercial one, and we place above it a shuttle with holes. This is done in order to reduce the rate of gold that is deposited. A lot of gold compromises the guidance. We also use a very low power of about 5 watts, and the deposition of gold is performed for a short time. All of this is done in order to avoid a lot of gold. And we finally obtained this island of gold. This image was obtained from an atomic force microscope. Normally this island have a height of about 10 nanometers, and the diameter that range from 10 to 40 nanometers, depending on the process we use. I would like to highlight two important mechanisms that influence the luminescence of the rare earth ions that are distributed all over the core and represented by black points in my figure. We have the short and long range enhancement mechanisms. At shorter distance, we have a large influence of gold nanoparticles, up to 20 nanometers distance from the island. So in this case, we assume the coupling of one rare earth ion with one gold nanoparticle. However, at larger distance, each rare earth ion feels the collective effect of the island field. So this is represented here. We have two different maximum associated to these two mechanisms that influence positively. They take place simultaneously and they influence positively the performance of the waveguide, leading to the increase of the relative gain, as we are going to show, in two different cases. In one of them, a waveguide prepared to operate at 800 nanometers. The other example refers to a waveguide prepared to operate at 1.53 micrometers, at the third telecommunication window. Well, starting with the one prepared to operate at 808 nanometers. In this case, the core was prepared using ytterbium and thulium ions, the same composition, of course, and it's a waveguide decorated with gold nanoparticle island. In this figure, I show you the experimental setup used. It's again the inside of this sputtering chamber. We have the two electrodes. Over one of them, we place the target of the matrix with pellets. Pellets are the small targets we produce, made of ytterbium oxide, thulium oxide. Over the other electrode, we have, as I said before, the commercial target of gold with that shuttle with holes placed above it. In this figure, I show you the core of the waveguide with a height of about 500 nanometers, the silicon dioxide pedestal with a height of about 1.5 micrometers. I'd like to highlight that in this case, the pedestal was prepared with the chromium mask, so using the steps I showed before. And here are the results of the relative again at 808 nanometers. We observe an enhancement of about 100% for a waveguide width of 30 micrometers, attributed to the presence of island of gold nanoparticles with diameter ranging from 10 to 40 nanometers. This result was obtained again by an atomic force microscope. And this figure illustrates to you the experimental setup used to determine this relative again, where signal and pump are multiplexed by a WDM, sent to the sample, and the signal is collected from the sample by a lancet fiber, a lancet especially produced for this experiment with 1 micrometer diameter, and the signal is finally sent to the spectrometer. Here is another result. A pedestal waveguide prepared to operate at the third telecommunication window. In this case, the core was doped with ytterbium and erbium ion. And I'd like to highlight that we use similar setup not only to produce the waveguide, but also to determine the relative gain. We observe here an enhancement of about 180% for a waveguide width of 6 micrometer due to the presence of this island with gold nanoparticle with average size around 4 micrometers. In this figure, I show you also obtained by scanning electron microscope, the profile of the waveguide with a high of about 400 nanometers. And in this case, the silicon dioxide pedestal has high of 1.2 micrometers. I also would like to add that in this case, the core was prepared without chromium mask. Well, as conclusion for future, we can think about different configurations for this waveguide. We can produce using nanolithography process, and we can conclude that this material is a potential one for different applications, as I could show to you. And finally, I'd like to acknowledge the National Institute of Photonics, the National Laboratory of Nanotechnology here in Brazil for the use of the transmission electron microscope. And I thank Escola Politécnica da USP for the use of the clean room to prepare the silicon dioxide pedestal. If you come to São Paulo one day, do not hesitate to visit us. Thank you very much, and here is my email in order to let you, if you have questions, if you want to obtain our reports, feel free to contact us. And here is our team, our students. Thank you again. Congratulations for the organization, and thank you for your attention.